Okay. I see there are folks still joining, so maybe I'll just say that if there are any questions from last week, uh, please ask me now. I'll wait for like maybe a minute, a few more minutes. I see there are still people who are joining, so uh, you can ask me now if you have any questions from last week. You can ask me later as well. Wait for some time. Okay. Uh, since there are no questions, so let us start today's session. So we are in week two, and um, we're essentially looking at since week one itself, we're looking at the basics of multivariable calculus. And um, so today, as usual, we're going to continue with the problem solving session. Um, okay. So we start off with this question on homogeneous functions. So I'll quickly define what a homogeneous function is. Uh, so before um, um, so before starting, how many of you were able to follow the lectures of of this week? Um, was there anyone who was able to follow the lectures of this week? Okay, I see some one person. All right. Yeah, it's ideal if you kind of at least glance through the material of the corresponding week before you join, and that way it kind of assists you in understanding the tutorial. So so let's say we have a function f from u to r, and this is a multivariable function in the sense that u is some subset of rn or r2, let's say, if you have a function of two variables, and u is basically the domain of the function. So whenever I write something like f is a function from u to r, then if this u is to be interpreted as the domain of the function. Um, depending on the context, if it's an n variable function, it would be Rn. U would be a subset of Rn. So we say that this function f is homogeneous if let's say it's a function of uh, of two variables. Then if you substitute f of lambda x plus f of lambda y, then that is equal to lambda to the power a of f of x comma y, where a is some real number. And and of course, this is subject to the requirement that uh, if if x comma y, if x comma y belongs to the domain of this function u, then for any scalar lambda, lambda x comma lambda y also belongs to this domain u. In other words, one can say, and this is not necessarily, this is just another way of saying it, is that u must be um, well, not necessarily u, but if you take the domain u and uh, then this particular set u, and if you do the factorization by lambda, then it is a subset of the real projective space. Uh, so here, so let's take a simple example. The simple example would be if you have a function of two variables uh, where x comma y goes to y by x. Okay. Of course, you require that x is of course non-zero. Uh, so let's say the domain of this function is r minus zero cross r minus. Let's say the domain of the function. Um, so this is of course a homogeneous function. If you substitute lambda to it, then you get something like lambda to the power a, but uh, this a is equal to zero in this case. So whatever this a is, uh, this a would be called the degree of this homogeneous function. So now, if you look at a particular example like this is fairly easy to solve. You just have to plug in f of lambda x comma lambda y in this function, which is something like lambda to the power 1 by 4 to the power 1 by 4 plus y to the power 1 by 4 on lambda to the power 1 by 5. Okay, and that's how you get the degree of this homogeneous function. Okay, I hope this is clear. This is a fairly easy problem to start with. Okay, so we are now going to move into some computational problems uh, involving partial derivatives. So before we start this, let me ask you. Um, yeah, someone has a question. Can you ask the
See,
question?
this is Praveen here. So
Yeah.
you explained that okay, lambda 1 by 4 by lambda 1 by 5. So this is the formula for degree of homogeneous function. So the answer will be like lambda 1 by 20, correct? See,
Yes. Yes.
okay. So this is the prerequisite. Okay, I got the point. Yeah.
Prerequisite. A prerequisite for what?
So for function to be the earlier you have explained that this is a like belongs to a rational number, and uh, the way we can recognize like f lambda x comma lambda y equal to lambda raised to a, then a, this is the homogeneous degree, and everywhere we figure out this kind of problem, this is how the way we can solve it.
Yes, yes. So not every function is a homogeneous function. Like let's say for example, if you have sine of x plus y, right? If you substitute lambda x plus lambda y, this is not a homogeneous function, right? Uh, so homogeneous functions typically, uh, like a lot, mostly homogeneous functions are functions which are of the form. Uh, so homogeneous functions typically take a form of px by qx. Okay, and what is p? Okay, I wrote x. I should be writing x comma y here. Qx comma y. So
Mhm.
these P and Q are basically they are homogeneous polynomials, generally speaking. So okay, so let's take this example. If you have two homogeneous functions, and if you take the symbolic quotient of those two homogeneous functions, that is also going to be a homogeneous function, right? This is the first observation. You get something like lambda to the power a, and let's say for another function you have something like lambda to the power b, then the degree would be equal to a minus b. So if you take the quotient of two homogeneous functions, um, but generally homogeneous functions are functions of the form some p by q, where this p is a homogeneous polynomial. So homogeneous polynomial is a polynomial in which the individual monomials in that polynomial all have the same degree. So um, so an example could be something like let's say you write xy squared plus x squared y. This is an example of a homogeneous polynomial because each term has degree three. So you're supposed to add the degrees of the two terms. But it need not just be a polynomial. You can also have something like rational powers in it. So so these P by Qs are actually polynomials, but not necessarily integer powers. You could have just rational powers on them. Okay. In fact, it's not necessary to just have rational powers. It's okay if you have real powers on them also. That's also fine. But the degree has to be the same. So it is, let's say. Uh, so let's say in its most general form, it can be of this particular form. So you have something like sum over of, let's say you are dealing with a function of n variables. You are looking at something like x1 alpha 1 summation of xn alpha n. And the sum is uh, over these alpha ones. Okay. These can be real numbers technically. And you have a finite number of sums, and not like an infinite number of sums. So alpha 1 to alpha n are basically tuples such that this alpha 1 to alpha n sum adds up to some number s. Okay, and you have a finite number of sums. But generally speaking, when we are dealing with homogeneous functions, uh, uh, we generally look at these a's where a's are generally some rational number. Generally, we do not look at irrational numbers when in looking at homogeneous functions. Uh, they are important. Okay, so why are these functions even important at the first place? So they are important in a number of situations. So, for example, maybe you have heard of differential equations, and uh, so if you are dealing with a function which you know is a homogeneous function, then it can assist you in finding solutions to certain differential equations. And these are partial differential equations, not ordinary differential. So they play a pretty important role. Okay, I hope it's clear.
You have taken an example like, okay, there is a option D also here. F is not a homogeneous. So while looking at looking at the equation right now in this scenario, we can figure out, okay, this is a homogeneous with degree 1 by 4 because it's a
Degree 1 by
directly
20.
derivable
Degree,
from x.
degree 1 by 20. Degree 1 by 20.
Yeah. So similarly, is there anything we can say like you have also taken an example like sine will be cannot be uh, directly as homogeneous sine of x comma y or something like that function.
Ha, ha, ha. Right, right. So yeah, I mean the idea is as follows. I mean, whenever you see this homogeneous function, you should try to plug in a constant like lambda and see if that thing factorizes out into lambda to the power a. It will always like there's no other way of checking it. If it factorizes out like this, then in a neat way, then it's a homogeneous function. If it's not, then it's not a homogeneous. Okay. There's nothing too fancy about it. It's not like it's not like you will run into a situation um, where you are kind of thinking whether this is going to be a homogeneous function or not. So the idea is that if you have well you can sort of think about it in this way that if you have two homogeneous functions, then you can add up you can the sum of two homogeneous functions of the same degree is going to be a homogeneous function. Okay. If you have two homogeneous functions and if you take the product of those two homogeneous functions, they are again going to be a homogeneous function. Similarly, you can take the quotient. That's also going to be homogeneous function. So maybe you're aware of a little bit of algebra. So it turns out that these homogeneous functions are a ring in some sense. Okay, it's a ring without necessarily a unity element, uh, but uh, uh, but it's a ring where you cannot add arbitrary homogeneous functions. Like if you have two homogeneous functions which are of different degrees, then that the sum of that would not be a homogeneous function. So this is some algebraic. So these are some algebraic properties of homogeneous functions which you can know from the outset. So let me just quickly write it down since you asked me. Um, if f and g are homogeneous of degree a, then so is f plus g. Uh, if f and g are homogeneous, not necessarily of degree A, they could be of arbitrary degree, then so is fg or f by g. Okay. Well, uh, you can also you can also do a bunch of fancy stuff with these. For example, if um, well, yeah, I mean anything that kind of preserves these scalars would also kind of preserve homogeneity. So let's say you're doing integration. Maybe you know some little bit of integration. That would also preserve homogeneity in some sense. So um, let's say let's say f and g are homogeneous functions, and I construct a bivariate function which looks like this. Okay. Um, so just give me. Yeah. Okay. Ah, uh, okay. So let's say um, I construct a function like this. Fxy is equal to this integral. Um, of course, you have to assume that the integral exists. So the domain of this capital F x comma y is chosen in an appropriate way, so that the integral exists and is finite. Then, if f and g are homogeneous functions, capital F of x y is also a homogeneous function. Capital F is also homogeneous.
Okay.
Homogeneous. Why? You have to do the same trick. You have to apply, let's say you substitute f of lambda x comma lambda y. Of course, this is all subject to the assumption that lambda x comma lambda y is a valid substitution. Um, right. And then you have integration of minus infinity to lambda y, f of lambda times x minus y, g of lambda y, dy. Okay. And now you can have this lambda popping out. But yeah, I mean, here there is a little bit of a problem because the integral will not satisfy this thing. So okay, so let's change this slightly. Um, Instead of doing this, let's have a function of a single variable. Um, well, no, not really. Sorry, I take back this example. I don't think this is correct because um, although you would have this lambda a over here, this integral need not this integral need not be something that leaves you with the correct answer. So yeah, this is not a correct example. I'll take back this example. Sorry. Um,
Yeah, but I got the rough idea, like
hmm,
the from the first example, like it is a
yeah.
kind of scalar multiple of that actual function.
Yes. The scalar multiple raised to some power of that of
Hmm.
actual function.
Correct, no?
Yeah,
So
that's
this
right.
is I try to correlate the things. Yeah.
Yeah, that's right. And it has some of these ring. It has a bit of ring-like properties to it. You can add them up. You can take products, divide them, and that will also give you homogeneous form. Okay. Right. So what happens if you try to integrate a homogeneous function? Let's look at that problem. It's an interesting exercise. Um, so let's say okay. Let me write it over here. Integrating a homogeneous function. So let's say f is a homogeneous function of n variables, x1 to xn, which satisfies f of lambda x1 to lambda xn is equal to some lambda to the power a f of x1 to xn. Okay. So now let us look at this integral over Rn of f of x1 to xn, dx1 up to dxn. Okay. Of course, we have to assume over here that this integral exists. Okay. So now what I can do is I can apply a substitution, like a change of variable operation. And a change of variable operation is basically this. I uh, I write x1 to be equal to some lambda times x1 dash. Okay, and for all from 1 to n. So xi is equal to lambda times xi dash. So now when you do a substitution like this, let us see what happens.
Uh-huh.
Integration over Rn f of lambda x1 dash up to lambda xn dash. Okay, and uh, then you have this dx1 to dxn, but you have to change this dx1 to dxn to dxi to dx1 prime. You have to change the differential term over here into the corresponding term. So the way you actually do it is that you have to look at the Jacobian of this transformation. So the Jacobian of this transformation is basically of the form lambda uh, lambda. Why? It's a diagonal matrix which has lambda in its diagonal entries. Okay.
Okay.
So this is the Jacobian matrix for this transformation. Okay. So the way you do it is that you write integration to Rn, then f of lambda x1 dash up to lambda xn dash. Then you put the determinant of this Jacobian matrix. So it's det of j, then dx1 prime up to dxn prime. Okay, uh, so this Jacobian matrix is basically lambda times I. In is the identity matrix. Okay, just give me 1 second. I'll just be back in 1 second. Yeah, sorry. Let's continue. Right. So the determinant of j, well, what is it? It is equal to lambda to the power n, right? So this becomes equal to integration of r to the power n f of lambda x1 dash up to lambda xn dash times lambda n dx1 prime up to dxn prime. Assume lambda is positive. Okay. Assume lambda is positive. So you're not putting a mod sign over here. But this is also a homogeneous function, so this term also comes out over here. So it's Rn f of lambda, sorry, lambda to the power a f of x1 prime up to xn prime lambda to the power n dx1 prime dxn prime. Okay. So what happens is that you get a term which is of the form lambda to the power a plus n, lambda to the power a plus n times this thing. But this is also the integral, right? F of x1 prime up to xn prime dx1 to dxn prime. This this term this term is actually equal to this term. Sorry, is actually equal to this term. So if this is I, this is also equal to I, right? This is just using a different symbol for the integration. I hope you understand this point. If you're doing an integration with respect to one symbol, and if you use a different symbol for the integration, then the integration remains the same. So just this part, just this part is just this part, but using a different symbol. Instead of using x's, we're using x1 primes to do it, right? The domain of this thing continues to be Rn only. But now what happens is that we end up getting this surface term over here, which is lambda of a plus n. Okay, so this is only possible if a plus n is equal to 0. That is, if a is equal to minus n. Okay, so in other words, if we have a homogeneous function such that the integral of that homogeneous function exists. Okay, so when I say the integral of the homogeneous function exists, what I mean is that if you integrate over Rn, then the integral exists for such a function. Then it is then it is a necessary condition that the degree of that homogeneous function be equal to the dimension, so the number of variables. Okay. So I hope you got this part. That's not going to hold for any arbitrary function, because if you give me any arbitrary homogeneous function, and if you tell me, oh, what happens if I integrate that arbitrary homogeneous function, it's not necessary that the integral will might exist over the whole Rn or over whole R2 for that matter. You can try with some examples. You can try construct some homogeneous functions of degree not equal to 2, let's say degree equal to 3 or degree equal to something, and then you can try to integrate that function. So let's say you take a homogeneous function, simple one. Let's say you take something like xy squared. Okay, this is a homogeneous function of degree 3, and let's say what happens if you try to integrate this over R2. Well, the integral is not finite. The integral is actually equal to infinity. So you cannot apply this particular treatment to this particular example, because this particular treatment requires that the function be actually finite. So basically the integral of the function be finite. Okay, then you can of course make a claim like this. Okay, all right. Um, so I hope this is clear. It was a good question. Okay. So the next question is with regards to partial derivatives. Um, Now, I'm not going necessarily into the definition of partial derivatives. I think you guys already know it. It's basically uh, it's basically requiring you to do differentiation, but keeping one of the variables fixed actually. Okay. So let's take this particular example. So you have u equals to tan inverse of some x squared plus y squared, yx minus 1. So here we come into this to this important uh, to this rather important um, uh, um, we have this important theorem which is called the chain rule in differentiation. So the chain rule basically says that if you have a composition of two functions, then the derivative of the composition would be the product of the derivatives. So which is to say that say um, say you have a composition of two functions f composed with g acting on x, and let's say I want to take the derivative of this. So d of f composed with g acting on x is equal to the product of the derivative. So it's equal to d of f at the point g of x times the derivative of g at the point x. Okay, so this is called the chain rule. And the chain rule carries over to multivariable calculus as well. So let me write this. Sorry. Chain rule for multivariable calculus. Say uh, f is a function from u to some r to the power m, and g is a function from some r to the power m to some r to the power n. Then if I consider the composition of the two functions, g composed with f, of course with an appropriate choice of domain over here. Um, Sorry, this will be r to the power n. So this is going to be a map from u to r to the power n. Okay, and so the chain rule says again that that the derivative of g composed with f. So let's say this u is some subset of r to the power k. So the derivative of g composed with f at the point x1 up to xk is equal to the composition of the derivative g dg at the point f of x1 to xk, then composed with the derivative of f d of f at the point x1 to xk. So this is the chain rule, and you have to apply the chain rule. Uh, and of course, the chain rule applies to more than one function. This is something, as you can clearly tell, this is a consequence of the theorem. Um, so here, in this particular example, why do we need the chain rule? Well, you have a function which is of the form u is equal to tan inverse of some function of x and y. So it's of the form some tan inverse of v of x comma y. Okay. So if you have to take the partial derivative, so del u upon del x, let's say, which we write in short as u subscript x. So this is del upon del x of tan inverse of v acting on x comma y. So the way you kind of look at this is that this is a composition, right? This is a composition of two functions, So this is del upon del x of tan inverse composed with v of x and y. Okay, so apply chain rule. So if you apply chain rule, this is first the derivative of tan inverse. So this is the d of tan inverse at the point v of x comma y times the partial derivative, sorry, times the derivative or at v of x comma y. But because the derivative is a partial derivative, you just take the partial derivative. If it was not the partial derivative, you had to take the full derivative. But here is the partial derivative, so you can just take the partial derivative. So this is del upon del x of v at the point x comma y. Okay. Uh, and then the rest is just computation, which you should be able to do. Okay. So I'm leaving this calculation uh, to for you guys to finish. So these are actually somewhat routine calculations computing these partial derivatives. But I'll still urge you to find these examples. You can look up any standard textbook on engineering mathematics. Let's say there's a crazy textbook that is a post recommendation. You can find many such examples in that crazy textbook, and then try to uh, compute those partial derivatives for stock functions. So stock functions would be polynomial functions, functions of powers and tangent-like functions, exponential functions. You can try to compute the partial derivatives of those guys. So partial derivatives, as you might know, it's like it's differentiating while thinking that the other variable is a constant. So you just treat the other variable as a constant and you do the differentiation. Okay. So to give an example, the partial derivative of this guy, uh, x squared plus y squared divided by x minus y. Let's say if this is my v, then uh, then del v upon del x is how I would do differentiation while thinking that y is actually constant. So this is equal to x minus y squared. Then then you take the derivative of this. So x minus y times the derivative of x squared plus y squared.
Oh, u by v. Okay,
Yeah, u by v.
u by v.
Uh, yes, plus x squared plus y squared times the derivative of x minus y. Okay. So sometimes I'll write this partial derivative operator as del x. This is going to be a short form for del upon del x. Yeah, and that's how you compute the partial derivative. And here it's a routine calculation. You have to sit and compute this, and you will get like a nice closed form expression which comes out to be equal to one of these four options. So I urge you to try this. This is a routine calculation. All right. So let's proceed.
So it's like a breaking the complex problem, resubstituting it, and then taking a derivative.
Uh, what do you mean by resubstituting it?
Like
Ah, okay, okay,
we
okay. Yeah, yeah,
we
yeah, yeah.
assume.
True, true, true. Yeah, so whenever you see, okay, so whenever you see a problem like this, you have to kind of you kind of have to understand what is going on, right? So there are two functions over here. So the first function takes x comma y and sends it to, well, I mean, you need not think about it as a composition of two functions. You can think of
Uh-huh.
it as a one function, but it helps you if you want to take the derivative. If um, just like if you have in the one-dimensional case from high school mathematics, let's say if you have a function like tan of sine of x, and if I ask you to take the derivative of tan of sine of x, the way you would think in your mind is that, oh, first I'm going to take the derivative of tan, and then I'm going to take the derivative of sine, right? So this is
Yes.
also a composition.
Yes.
This is like x first goes to sine of x, and then the sine of x then goes to tan of sine of x, right? So the derivative, the chain rule is basically saying is that you can take the derivative of this operation, and then you can take the derivative of this operation, and then you can compose the two. Okay, that is going to be the derivative. So yes, as you said, it is about recognizing that the complex problem can indeed be written as a composition of parts where individually I can compute the derivative of those parts. Okay, that's right. What you said. All right. So let's move to some other problem. So, by the way, I mean, have you guys been able to follow the lecture material of the course? Maybe not from week two, maybe week one only. And have you found any issues, any troubles where you were not able to understand any particular lecture material? You can feel free to ask me. Uh, fine. Right. So this problem is well. Sorry. Oh, okay. Wait. Yeah, I have already done that. The recorded session is already available. I'm surprised that you're not able to find it. Um, okay, I'm surprised that the recorded session. I've already shared it. I don't know why you were not able to find it. I can give you the link to the video. This is the link to the video. Right. All right. Let's proceed. Right. So you have a problem, u, where u is here x squared plus y squared upon x cubed plus y cubed. Yeah. So again, the you have to compute x ux plus y uy. So let's see what x ux is. So let's say what ux is first. U is equal to x squared plus y squared upon x cubed plus y cubed. Then ux is equal to x cubed plus y cubed squared times uh, the numerator is x cubed plus y cubed, and then you take the partial derivative of the numerator with respect to x, which is twice x, minus this term x squared plus y squared, and then you take the partial derivative of the denominator with respect to x. which is 3x. Okay? So this turns out to be equal to 2x cubed plus 2xy cubed minus 3x cubed minus 3x squared y squared. Okay, so this is equal to some 2xy cubed minus x cubed. Sorry. This is 2x to the power 4. Sorry, sorry. This 2x to the power 4. This is 3x to the power 4. Right, so this is equal to 2xy cubed minus x to the power 4 minus 3x squared y squared upon x cubed plus y cubed. So this is the ux basically. And likewise, you are supposed to compute uy. Um, yeah, I mean, because everything is just symmetric, you can just interchange x and y. So uh, so you can just interchange x and y and get uy to be equal to qx cube um, y minus y to the power 4 minus 3x squared y squared divided by x plus y, right? And then you basically computing this algebraic identity x ux plus y uy, and that's going to be equal to some constant multiple of u. It's going to be equal to a constant multiple of u. This constant multiple is k, and you're supposed to find out the value of k. Okay. So I leave it as an exercise to finish this calculation. All right. So far, no doubts. So look at.
So just the step remaining is substitute the in the
Yeah, yeah.
formula and just get
Yes,
the value.
that's right. That's right. Um, so now let's come to a different kind of problem, so-called stationary points. The question is, what are the stationary points of fx? Okay. And the okay, just give me 1 second. So the stationary points of function fx, uh, basically, that's just uh, asking you to say, asking you to find out what are the points where the derivative vanishes. So the set of points where the derivative of a function vanishes. Uh, okay, so let me just write it over here. Definition: the set of points where the derivative vanishes, they can be called stationary points. They can also be called critical points. It's just a different name for the same thing. So here, of course, this is a function of one variable. So you can take the derivative of that. So d of f at x is equal to x squared minus twice x minus 3. And so if you have to compute what are the stationary points of d of f(x), then you have to equate this to 0, and then you have to find the set of points where this equation is equal to basically where this equation holds. And that would give you the stationary points of a function f. Now, what happens if we are looking at a function of multiple variables? So, say say f from u, which is a subset of, let's say, R2 to R, is a function. Of course, when I'm saying function over here, you have to understand that the function is a function where you can take derivatives. So it's yeah. We discussed about the existence of derivatives in the previous lecture, in the previous tutorial. So f is a function that, of course, admits derivatives. Otherwise, there's no question of talking about derivatives at the first place. So so f is a function u to r. Right. And I asked, so the question is, what are the stationary or critical points of f? So let's write it down, definition. Then the critical points slash stationary points of f are those where d of f vanishes. Okay. Now, basically, what is d of f, right? So d of f is a, if f is a function of two variables, then d of f is basically a 1 cross 2 matrix. So d of f is a 1 cross 2 matrix. And the entries of this matrix are del f upon del x and del f upon del y. Okay, so this is called this is the derivative of a function of two variables. If you have a function of of n variables, then the derivative would be just the corresponding partial derivative. So it would be del x1 f up to del xn. Okay. Now what we are saying is that we want the critical points of f to be the set of points where this derivative vanishes. The derivative vanishes is equivalent to saying that this 1 cross 2 matrix must vanish. So a 1 cross 2 matrix vanishing is just saying that the entries must vanish. So uh, d of f vanishing means the entry is vanishing. That is, del x upon del f upon del x should be equal to 0, and del f upon del y should also be equal to 0. Okay. So the set of points x and y where del x of f and del x of del y of f are both equal to 0. So We write it in set theoretic notations. The set of points x comma y such that del x of f and del f of y are both equal to 0 is the set of critical points or stationary points. Okay, so let's take one example. So the question is, what are the stationary points of this function? So here you have to take del x of f and del y of f and equate them to 0. Okay, so so what is del x of f? Del x of f is equal to 6x squared plus 6y squared minus 150. Okay, so if we equate this to 0, so del x upon f equated to 0 implies that x squared plus y squared is equal to 25. Okay, now what is del y of f? Del y of f is equal to um, 12xy minus 9y squared. And if we equate that to 0, get y times 12x minus 9y. So the rest is just solving this system of equations, which is very easy to solve, right? So just solve this system of equations. X squared plus y squared is equal to 25, and y 12x minus 9y. That would give you the set of critical points.
Okay.
Okay, so I hope you'll be able to finish the computation. Otherwise, I can sit and do it. So there are two choices, right? Either y is equal to 0 or 12x is equal to 9y, which is just saying that 4x is equal to 3y. So if y is equal to 0, then you have x to be equal to plus or minus 5. So so rather two critical points are plus or minus 5 comma 0. The other set of critical points are given by 4x is equal to 3y. So if you substitute y is equal to 4x by 3, then you get x squared plus 4 by 3x squared is equal to 25, which is 25 x squared is equal to 25 times 9. So x squared is equal to 9. So x is equal to plus or minus 3. If x is equal to plus or minus 3, then y is equal to plus or minus 4. Okay, so the two critical points, so there are four critical points, plus or minus 5 comma 0, and the other critical point is um, plus or minus 3 comma 4. Okay, right. So this is how you're supposed to find the set of critical points. But um, now the immediate question is, if you um, if you have a function of a single variable, then the set of critical points can come out to be oftentimes the set of critical points or the points where this derivative vanishes often turns out to be well. I mean, if the function is not well, I mean, generally the critical points in a lot of these cases comes out to be isolated critical points. So when I say isolated critical points, what I mean is that the set of points where the derivative vanishes uh, is basically a discrete set. Let's take an example what a discrete set is. So let me give you an example. This is the definition of a discrete set. So U, which is a set in R, let's say, or some R to the power n could be, is a discrete set if for all points P in U, there exists a neighborhood. There exists a neighborhood of P, let's call that UP, which is a subset of Rn, let's say, yeah, which is a subset of Rn, such that UP contains no other point of U, which is equivalent to saying that U intersection UP is just this point P itself. Okay. So an example of a discrete set is basically like this. Let's say uh, your uh, your space is this whole R2 plane, and I draw a bunch of isolated points. Okay, so that would be an example of a discrete set. Okay, uh, it's called discrete or isolated for precisely this reason that for each point P, you can draw like a small ball around it, which contains no other point apart from P only. Okay, an example of what is not a discrete set, let's say, is something where this property does not hold. Um, let's say the graph of a continuous function is going to be, for instance, not a discrete set. Or let's say if I compute this circle, let's say uh, x squared plus y squared is equal to 1. This is not a discrete set. Okay, because there is whatever if you choose if you choose whatever point you choose over here, uh, if you draw a neighborhood, then it's not separable from the other elements of uh, of the set circle. Okay, so this is an example of what is not a discrete set. Now the
Any
question is, yeah,
I not able to relate about the graphical view of the discrete set. Like, it's not separable. It means like
no, not
it.
separable is not like a mathematically rigorous term. What I mean is that like if you draw a small ball around any point in on the circle, then this ball
Mhm.
will always have some other point of the circle, right? Like however small a ball you choose, and if you draw a circle, then you will always find that um, that it always has some other point of the uh,
Like it contain the part of the bigger one.
it contains a part of the set. Yes, that's right. It will always contain some part of the set. So therefore, it is not a discrete set. A discrete set is what we mean by literally being discrete. That the points are are kind of out there, separated, and you can always like in a very loose sense, there are gaps between the points. That is a discrete set. If there
Okay.
aren't gaps between the points, then the set is not a discrete set in a very loose uh, sense. Okay.
Okay.
Um, right. So I mean, if you ask me like computationally, what is a discrete set and what is not a discrete set, there's no one mathematical formula which can tell you if a given set is discrete or not. It depends on various cases. Um, right. Okay. For instance, again, discrete sets will have the property that if you have two discrete sets and if you take the union of two discrete sets, it's again going to be a discrete set. Okay. If you take the intersection of two discrete sets, it's again going to be a discrete set. So discrete sets follow your typical set operations like union, intersection, set difference. These are always going to end up giving discrete sets. So again, if you again have to ask, if you're given a problem whether something is a discrete set or not, you may have to break it down into small parts, and then you may have to rely on these set operations to determine if a set is discrete. But the point is not that. The point is, when can we say that the critical points or the stationary points of a function is a discrete set? Okay, it need not always be a discrete set, right? And and the best example is basically given by this. Um, so the question is basically question: uh, Can the set of critical points of a function not be a discrete set? Okay, so let's say if it's a function of two variables, so we are basically asking that if we solve del x of f equal to 0 and del x of y, sorry, del y of f equal to 0, then the solution to this system of equations comes out to be not a discrete set. What we're essentially looking at is the solution set of this system of equations. But the question is it necessary that it's always going to be a discrete set or not? Like, can it be not a discrete set? And the answer is yes, it very well may not be a discrete set. So let's take an example. So let's say del x of f is equal to some x squared plus y squared. Okay. Um, yeah, let's say it is equal to some x squared plus y squared. And del y of f is also equal to x squared plus y squared. Is that possible? Well, not x squared plus y squared. That's a bad example because you have a solution already.
Mhm.
Let's say del x of f is equal to x plus y, and del y of f is also equal to x plus y. Is it possible to have a function where del x and del y of f are both equal to x plus y? The answer is yes. Definitely, we can have such a function. So the way to the what function can give you a partial derivative which is x plus y and x plus y in both cases. So your f may be equal to um, some um, some half times x squared plus plus let me check, plus yx plus some half times y
Y
squared.
square.
Okay, so this is a function that will give you a, partial derivative which is both x plus y and x plus y.
Uh-huh.
So now if you solve this thing, So now if you solve del x of f is equal to del y of f to be equal to 0, you get x plus y to be equal to 0. But x plus y equal to 0 is not, so the set of points in R2 satisfying x plus y is equal to 0 is not a discrete set, right? It is basically a line. The line, it is the equation of the line satisfying x plus y is equal to 0. So if you have to plot this set on in the R2 plane, so this is basically y is equal to minus x. So this basically this line. But this is not a discrete set, right? Obviously not a discrete set. So it's not always necessary that the set of critical points of a function f uh, be a be a discrete set. So now you can obviously ask the question: Is it possible that uh, so is it possible that del x of f and del y of f are not the same? So here I took like a particular example where I have chosen del x of f and del y of f to be the same function. We can of course ask the question: Can they be different? Uh, can del x of f and del y of f be be non-identical functions and still right and still uh, the set of points f and still f uh, is a non-discrete set. Sorry, and still um, crit of f crit of f is the set of critical points of f is non-discrete. Okay, that's an interesting question, and to be honest, even I don't really know the answer to this question. Um, I'll have to think about it myself. Um, but maybe you can ponder on this question. Um, to be honest, I don't know. I think the answer is yes. We can definitely have uh, we can definitely have del s of f and del y of f to be a non-identical functions, and still as such that the split of f is going to be non-discrete. So essentially, what we require over here is that um, right. Hmm. So it's an interesting problem, definitely. Um, yeah, I'll have to think about it. It's definitely interesting problem. Can you cook up some example where del x of f and del y of f are non-identical, and still the set of critical points is non-discrete? I leave it as an exercise. You can think about it.
Mhm. Okay.
All right. Um, let's move on. Okay. this problem is again a computational problem, and it involves taking mixed, taking basically second order partial derivatives. So second order partial derivatives are defined analogously to second order derivatives in the sense that it is repeatedly taking a derivative. So if you have a function f of two variables x and y, then we often write this as del square f del x squared. Sometimes we can write it as del xx of f. Sometimes you can also write it as fxx. So this just means taking partial derivative twice. So it's del upon del x of del f upon del x. So treat del f upon del x as a function in x and y. So the idea is that treat uh, del f upon del x as a function of x and comma y, and take partial derivatives as usual. Okay. Um, okay.
In
I just yeah. Say please go on.
Z, here it is all function is written as z is of x function of x plus y, then again y g
Hmm.
of x plus y.
Yeah, yeah. So again,
Okay.
the way, so let's say if you look at f of x plus y, and if someone asks you what is the derivative of so what is del x of f of x plus y? So uh, so I mean, there's no other information given to you. So
Hmm.
when you see something like this, z equals to x of f of x plus y equals to g of x plus y, you can assume in this case and for generally for in the context of this course that f is a one variable function. That f is basically a function from R to R. Okay, it need not actually be a function from R to R, but here you can always assume that f is a function from R to R. All right, and so if you have to compute del x of f of x plus y, well, if you have to break it down and really understand how you're supposed to take the partial derivative, well, this is the chain rule again, right? So this is a map. So the map, what it is doing is that it is taking x comma y and first sending it to x plus y, right? Which is so x comma y. This is basically a point in R2, and sending it to x plus y, which is basically a point in R, and then f operates on this guy and gives f of x plus y. So by the chain rule, if you are supposed to take the derivative of this thing, you take the derivative of this and the derivative of this, and the derivative of f, and then you compose it. So that is equal to d of f at the point x plus y composed with the derivative of this map. But instead of the derivative, you take the partial derivative. So it is basically the partial derivative of this map x plus y, which is just equal to 1. So this is equal to d of f at the point x plus y. So this is going to be a partial derivative for f of x plus y. Similarly, you can compute the partial derivative for g of x plus y. That would be equal to dg at the point x plus y. Okay. So what is so what is z? So z is equal to x of f of x plus y plus y times y times g of x plus y. Now, okay, now you would have definitely heard of what is called the Leibniz rule in in high school calculus, which is that if you have a product of two functions f and g, then yes, exactly. So here again you have to, so the Leibniz rule applies to the partial derivative as well. So partial derivatives behave very similar to, and just partial derivatives behave very similar to your ordinary one derivatives of one variables. So you can apply the Leibniz rule. So the Leibniz rule, when applied on this summand, would be equal to f of, okay, so let's say I am doing this. So let's say I'm doing del x of z. So del x of z, I'll first apply this on this summand. So that is del x of x times f of x plus y plus del x on y of g of x plus y. And what do I get? Well, um, well, according to the Leibniz rule, I first differentiate this term, so which is 1. So this is equal to f of x plus y plus x times the partial derivative of f of x plus y, which we just computed. That is just equal to d of f at the point x plus y. Okay. Then similarly, for this term again, here y is a constant, so there's no point in doing this. So y just comes out, and then you take the partial derivative of g. So this is just equal to d of g at the point x plus y. Okay, fine. So that is equal to your del x of z. But here we are looking at uh, we are looking at functions of two variables. Sorry, we're looking at higher order, second order partial derivative. So what is del xx of z? So this term, so this del xx of z uh, is is the partial derivative del x of del upon del x acting on del x of z. Okay, so you have to take a partial derivative again of this expression. So again, this comes out to be equal to d of f acting on d of f at the point x plus y plus, again you apply Leibniz rule over here. So that would give you d of f again at x plus y plus x times. Now you have to take the second partial derivative of del f of at the point x plus y. So
So
that
double
would be,
derivative.
yes, yes. So what is this term is my question. So this term, let us quickly compute it on the side. So del x of df at the point x plus y is, again you basically apply the Leibniz rule. So so this is a composition of two maps. X plus y goes to x plus y, and then x plus y goes to d of f at the point x plus y. So if you have to take the derivative, you take the partial derivative here and the derivative here. So the derivative term over here would be d to f, which is just another way of saying f double dash. So it's just f double dash at, and the derivative term over here is just 1. So this is just equal to f double dash of x plus y. Okay. So you can substitute this back. So this is equal to x times f double dash of x plus y. Okay. Plus again this term. So this is y times g double dash of x plus y. So this is 2 times f dash x plus y plus x times f double dash of x plus y plus y times g double dash of x plus 2. Okay. Um, Similarly, you can compute y of. Similarly, you can compute this term. So this is del xx of z. Similarly, you can compute del yy of z, right? Um, you can compute this term. What else do you need to compute? We need to compute next uh, del square
dxy.
z and del xy. Okay. Now the interesting question comes is uh, so basically this is equal to saying that you take del upon del x of del z upon del y. Okay. This is what this comes out to be equal to. So you have to first take del z upon del y, and then you have to take del upon del x of that. But if f and g are are functions for which uh, are functions where second order partial derivatives are continuous, okay, then it does not matter what is the order in which you take the partial derivative. So let me write it down. If 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 z has continuous second order partial derivatives, that is if del xy of z and del yx of z are continuous, and not just these terms, also these terms, del xx of z and del yy of z. If all these guys are continuous, then you require then it is a actually this is a theorem. I should not just state it like that. This is a theorem. Then del xy of z is equal to del yx of z. So it does not matter what is the order in which you take the partial derivative. So here, what you can test is that you can first do del z upon del y and do del upon del x of that, and you can otherwise you can do del upon del y of del z upon del x and check if you get the same expression. You will get the same expression. Okay. Um, okay. So here it does not matter what is the order in which you take partial derivatives. It will not. It's the same. Of course, we are assuming over here that uh, that F and G are admit continuous second order partial derivatives, which is saying that F and G belong to this class of functions which are called C2 functions. So if F and G are C2, then yeah, you can doesn't matter what is the order in which you take. So yeah, so I leave it to you to compute to finish this calculation. Uh, you can calculate del x as del y. Similarly, you can do del y by del z. It's just routine stuff, and and then you can take the second order partial derivative as well, which is just saying that you take this uh, del x del x of z, and then you take del y of that. So you can take this expression and apply del upon del y on this. That will give you uh, del del y. Sorry, that will give you del yx of z, which is basically what you need over here. Although this is del xy of z, but as I said, del xy and del yx would be the same over here. All right. If there are any questions, you can always ask me. All right. Let's go ahead. Hmm. Let's next look at types of critical points. Still have two still have like two important stuff to kind of finish off over here. Okay, so let's look at types of critical points. Okay, so let's say we are given a function in two variables, and we ask you to compute the maximum of this. So let me take a quick detour and quickly explain. So you know what how to compute stationary points. So stationary points are basically those points where the partial derivative vanishes. So I'm going to often write it as equal to crit of f. Crit of f is a set of critical points where the partial derivative vanishes. So x comma y such that del x of f is equal to del y of f is equal to 0. Okay. Um, Now, of course, the question is how to determine whether a critical point is a maximum or a minimum, right? Um, Let me first tell you what happens for the multivariable case. In the multivariable case, a critical point. So in one dimensional case, what you know is that a critical point can either be a maximum or a minimum. So like if I just plot a graph quickly, so let's say you have some function which is of this kind. Okay, so then maybe you can say that the function has two critical points, maybe one here and one here. One is a maximum and the other is a minimum. Okay, so there are two types of critical points for one dimensional function, either maximum or minimum. When you're looking at higher dimensional functions or multivariable functions, critical points need not just be maximum and minimum. There can be what we call saddle points. Okay, so um, okay, so how do you determine something is a maximum or something is a minimum? So something is a minimum if um, okay, so if something is a maximum, then the way we do it in one-dimensional calculus is that, so let's say f is my function, which is a function of a single variable. I do something called a second derivative test. So I do f double dash of x. Let's say let's call this point x1, and let's call this point x2. I do f double dash at x1, and if f double dash at x1 is negative, I say that f x1 is a maximum. Okay. If f double dash of x2 over here is positive, then I say that um, x2 is a um, um, x2 is basically a um, x2 is basically a minimum. Okay. Now, what happens? So, essentially, what we're doing is that from the first derivative, it is not possible to determine whether a critical point is a maximum or minimum. You have to take a second derivative. All right. And why do we have to take a second derivative? Well, that's because when you write the Taylor expansion of a function, then the Taylor expansion of function. Well, what does it kind of look like? So it is equal to f of x. Um, well, that is equal to f of x plus some delta x is equal to f of x plus f dash of x at the point delta x plus times delta x um, plus delta x squared by 2 factorial f double dash x and so on. Okay. Now, now, in a very loose sense, again, this is not a strict mathematical proof for that, but when f dash x is equal to 0, which happens at critical points, then in order to determine whether the function is locally increasing or locally decreasing, you have to make use of the second order term. Okay, so it's no longer enough to take a first order approximation. We have to take a second order approximation of that particular function. Okay, and and when we are taking this second order approximation of the function f, then the sign of f dash x becomes f double dash x becomes important, because anyway this term is zero at the critical point, and if f double dash x is if f double dash x is negative, that means that around this point x1, if I take like a small second order approximation of f, then all the values of f x plus delta x, then f of x plus delta x is actually smaller than f of x up to a second order, up to a third order um, error term. So there's going to be like a third order error term, which is some small o of x cube. But if we ignore the third order error term, and if we just stick to second order, up to the second order, then f of x plus delta x would be less than f of x at the point x1 if f double dash x is negative, which is why we take this second derivative test. Similarly, for at the point x2, we would have that f double dash x would be positive, and so if you take a second order approximation around the point x2, uh, all the points f of x plus delta x would be greater than f of x, and so x2 would become a local minimum of that function. Okay. Now the question is, what happens for functions of two variables or functions of higher any number of variables? So let's just look at functions of n variables. So if we have a function of n variables, um, so f is some function of u, which is a subset of Rn to R. We are going to assume over here that f admits a second derivative. If f does not admit a second derivative and all those nasty things, then we're not going to worry about those kinds of problems here. So we're going to assume over here that f is a C2 function, C2 of u, which means that f admits continuous second order derivatives. So then the critical point of f, if C is a critical point, if C is a critical point of f, then we have del x of f, del x1 of f up to del xn of f is equal to 0 at C. Now to determine if what is the kind of critical point of C, we have to take the second order derivative. So the second order derivative, uh, so the first order derivative is, what is that? So this d of f is a 1 cross n matrix. It's a 1 cross n matrix whose entries are del x1f up to del xnf, right? So the second derivative of f, which we will call d2 of f, there's a term for it, is called the Hessian of f. Okay, and the Hessian of f is a matrix. It is an n cross n matrix whose ijth term, so Hessian of f, the ijth term of this Hessian of f is equal to del x, sorry, is equal to del xi del xj of f. Okay. Now, if f is a C2 function, then Hessian of f is a symmetric real matrix. Okay. Why? Because Hessian of f at ji is equal to del xj del xi of f, which is just equal to del xi del xj of f. So the Hessian of f, so let me just write it over here. If f is C2, then Hessian of f is um, is a symmetric matrix. All right. Now the question is, for the one-dimensional case, we have taken the um, we have taken the second order derivative, and we've looked at the sign of that second order derivative to determine if something is a maximum or a minimum. Now, what happens if you're looking at these? Now you do not have just a scalar number; you have a matrix. You have an n cross n matrix. So let's bring it down to the two variable case so that it becomes kind of it looks less abstract and sort of looks manageable for now. So for a two-dimensional function, this Hessian of f at a point x comma y is equal to del x x f del x y f del y y f and del yx of f. Okay, these two of course are equal. So you have a 2 cross 2 matrix, and now we have to determine if if at a critical point C, what how do you determine if something is a maximum or a minimum? So so let me first draw an example, and then I'll tell you how to determine what kind of critical point it is. Okay. So what happens, unlike the one-dimensional case, in the two-dimensional case, there exists three possibilities. Okay. So an example is like this. So let's say I I compute so let me compute the graph of a function of two variables. Okay. Um, let's say the graph looks something like this. Sorry. Okay. So let me compute. So let's say this is the graph of some function. Okay. Um, so then, I mean, you should think of this as a as like a bowl or something like that. This is like a parabola. Yeah, this is not a 2D figure. So if you look at this point, so then at this point is a minimum. Why? Because if you, however you take a, if you take this point P, and if you take a neighborhood of the this particular point P over here, then the function value is always bigger than the function value of this point. Okay. So however you take, So essentially, what it means is that in whatever direction you move uh, from this point P, so let's say this is my critical point C, and if you move in any particular direction, uh, then you will always see that the function value decreases, at least locally. Okay, so C is a minimum. If my, let's say, the opposite case was, let's say, the graph of my function looks something like this. Let's say this is the graph of my function. Again, this is supposed to be interpreted as like a 3D figure. Okay, now this is the point. Now, whatever direction you move in over here, um, this is still going to uh, this is still going to um, I mean, yeah, this is still going to cause a decrease in the value. So this is a maximum. Okay, but now let me draw another example of a graph, and this is the very well known horse saddle. So right, so the horse saddle looks something like this. It is basically this. Sorry, no, no. This, and then it looks like this. You take this point over here. Okay. Uh, well, I mean, the way to sort of plot this, draw this is kind of like this. So you have something like this over here, something like this over here, and
So this bring up to the local minima and local maxima point
yes, yes.
in a
But here, this is a
curvature.
no. The here the thing is actually very tricky because oh no, not this one. I plotted. Yeah. Sorry. Okay. Um. Okay. Let's take a point like this over here, and let's let's assume that the thing is like this. Yeah. So this is how my curve. This is the equation of my this is how the graph of my function looks like, and this is a critical point C. But this critical point is very interesting because if you move along this direction, then the function value is increasing. But if you move along this direction, then the function value is decreasing. Okay. So these kinds of critical points where along some directions the function value is increasing and along some directions the function value is actually decreasing, they are called saddle points. Okay. Now, okay, so geometrically the picture is clear in that in two variables, you may have minima, you may have maxima. So minima maxima are similar to the one-dimensional case, but you may also face this. You may also come across this situation where a critical point is such that along some directions, the function value increases, and along some directions the function value decreases. Okay, and so how do you determine whether at a particular point the function value is increasing? So how to determine what kind of critical point it is? In order to answer this question, we can do whatever we did for the one-dimensional case. We wrote down the Taylor series expansion. Here also, let's try to write down the Taylor series expansion. So if you have f of x plus, sorry, if you have a point x comma y, and I look at a small deviation which is h. So h is a vector which is equal to h1 comma h2. Then f of x plus h1 comma y plus h2 is equal to f of x plus h1 times um, del x of f plus h2 times. plus h2 times del y of f plus, now this is where the second order term kicks in. The second order term is equal to half of half times, you write this vector h1, h1, h2, write this as a matrix, then you write the Hessian of f, this is a matrix, and then you do take this one, h1 times h2. And then there are third order terms. Okay. Now,
Mhm.
now of course, if x comma y is a critical point, then these terms drop to zero, and you're looking at f of x plus this particular term. All right. So this particular term is it's basically what we call a it's a symmetric bilinear form. Hessian of f is a symmetric bilinear form, and you have this bilinear form which is evaluated at the vector h comma h. So Hess of f is a symmetric bilinear form which is and we evaluate it at this vector h. So it's basically S of f evaluated at h comma h. Okay, which is basically this expression only. Now, of course, this expression may not be positive. It may be positive. It may be negative. It can have. It may be positive. It may be negative, depending on how you choose this h. Okay, okay, but uh, but the question is, if Hessian of f, if this expression is always positive, if Hess of f at h comma h is always positive, independent of h, then this is a minimum. If this guy is negative, then this guy is a maximum, irrespective of all h. Okay. But if there are some values of h where it is positive and some values of h where it's negative, then it is a saddle. Okay. And to determine whether it's a saddle or not, what you need to do is basically this. So you look at a Hess of f and you compute the eigenvalues of this. If the eigenvalues are positive, if all eigenvalues are positive, it's a minimum. If all eigenvalues are negative, it's a maximum. If you have an eigenvalue which is positive and an eigenvalue which is negative, then it's a saddle. Okay. So
Uh, can we again? I might be misplaced the conversation in between. Can we again, if it is over, then can we again once shortly go through again from the start
yeah.
for this?
Yeah. So what we have to do over here, I mean, we have talked a lot of things. So
Yeah,
we
yeah.
have to take a second derivative. So like one variable case, we have to take a second derivative for the two variable case.
Uh-huh.
Now, when you take a second derivative, you will no longer have a number, a scalar. Instead, you will have a matrix. You will have a two cross two matrix, which we call the Hessian of F. And this two cross two matrix is this matrix of mixed of partial derivatives, which is
Mhm.
del xxf, del xyf, del yxf, and del yyf. Okay. Now, once you have computed this Hessian of f, you have to compute the eigenvalues of the Hessian of F. You can always compute the eigenvalues of Hessian of F because it's a real symmetric matrix. So you will always get real eigenvalues. There will be no complex eigenvalues for this particular matrix. So once you have computed the eigenvalues of Hessian of F, you need to check what are the signs of the eigenvalues. If the eigenvalues are all positive, it's a minimum. Similar to your 1D case, if everything is positive, the second derivative is positive. So the way you interpret it plus means that the second derivative is positive, so it's a minimum. If all the eigenvalues are negative, it's a maximum. But if you get an eigenvalue which is positive and an eigenvalue which is negative, then it is a saddle. What happens if you get an eigenvalue which is zero? Okay, is it possible? Yes, it is definitely possible that you may get um, you may get a um, yeah, it is definitely possible that you may get an eigenvalue which is zero. So if the eigenvalue is zero, then this Hessian test fails. All right, then the Hessian test fails, and you have to look at a third order term in order to determine whether the function is what kind of critical point it is. But we're not going to encounter that in this course, hopefully. In this course, whatever critical points that you are going to look at, they are going to be critical points where the Hessian of F does not go to zero. Like the Hessian of F does not have a zero eigenvalue. Okay, so that's basically a degenerate case. So we're going to assume that we're not facing this degenerate case. So you look at the eigenvalues and then you determine if it's saddle or not. Um, so let's take this example only. So uh, what is this? F is equal to 2 minus x squared minus x point minus 5. So you have to first determine the critical points of F. So in order to determine the critical points of F, you first do del x of F equal to 0, which is saying that um, twice x plus y is equal to 0. Then you do del y of F. So del y of F is equal to minus x minus 3y squared equal to 0. So you solve x plus 3y squared is equal to 0. Okay. So quickly, let's try to compute a solution. You have 2x, you have y is equal to minus 2x. You plug this in, so you have x plus uh, x plus 3 times 4x squared is equal to 0. This is 12x squared plus x is equal to 0. So x is either equal to 0 or x is equal to minus 12, right? And so if x is equal to 0, then correspondingly y would also be equal to 0. So 0 comma 0 is a critical point. The other critical point is minus 1 by 12 comma 1 by 6. Okay, so you get two critical points. What does this question say? It says 0 comma 0 is a stationary point. So they're interested in 0 comma 0. We're not interested in the yeah. So we're not interested in the other critical point. We're interested in 0 comma 0. So if this is the case, then you have to compute the Hessian of F. So the Hessian of F is well, what is that? So you take the second derivative of this. The second derivative of this is 2. Again, you take the second derivative of this. Oh no, wait. That's my mistake. So sorry, minus twice x minus y. Sorry. This is so del of f is equal to minus twice x minus y. So if you take the second derivative, that's equal to minus 2. Similarly, here it is equal to minus x. Sorry, yeah, here it is equal to minus x minus 3y squared. So if you take the second derivative, that is equal to minus uh, 6y. Okay, and uh, and del x del y uh, is equal to minus 1 here, and del y del x is also equal to um, minus 1 here. Okay, now uh, now of course at the point 0 comma 0, this term is 0. So the Hessian over here is minus 2 minus 1 minus 1 0. Okay. Now you have to take the eigenvalues of this thing of uh, of uh, of this matrix. So uh, this is my each of f. So you have to solve the eigenvalue equation, which is h of f minus lambda I2 is equal to 0. So that is equal to determinant of minus 2, sorry, determinant of minus 2 minus lambda minus 1 minus 1 uh, minus lambda. You can take the minus sign out, not a problem. That gives us determinant of 2 plus lambda 1 1 lambda. So this is equal to lambda times lambda plus 2 0 0. Okay, I think this is the plus. I'm making a mistake somewhere in the computation. Uh, so what are the roots of this equation? Okay, I mean, whatever it is, you determine the roots of this equation. Uh, and
Seems
that
to
will
be
basically
minus
tell you,
1 minus root 2.
okay, minus 1
Minus
minus root
1 root 2 or minus 1 plus
2.
root 2. Yeah, like
Okay,
that.
yeah, I mean, you have to finish the computation here and see what are the roots of this
Hmm.
equation, and that will determine whether what kind of critical point 0 comma 0 is. Okay, uh, that's how you solve it. Okay, I think we are out of time today, so we'll stop here. Um, yeah, I think we have it covered, whatever was there to be covered. We have these questions on what is a local minimum, local maximum. You determine something is a local minimum, local maximum based on this Hessian test. This is called the Hessian test, basically. Take the Hessian, take the eigenvalues, and then check which is what. Okay. So I think I'll stop here because we are out of time. If you have any questions, then you can ask me now. Otherwise, I'm going to leave in next 2 3 minutes.
Nothing as of now.
Okay. Yeah, put that.
Any short reference book like whatever we the video we will again revisit the video in YouTube.